well, and that's why Nitika ma'am took your last chapter. Hope it was a really interesting one. All right. Now, chemical bonding, this chapter, right, is even more interesting, right? Chemical bonding is super important. Chemical bonding is super interesting, quite crazy, in fact, right? But then again, it is going to be really fun. It's going to test out the powers of your imagination, the powers of your visualization, and we are probably, I hope we are going to have a lot of fun during this chapter. All right. So without wasting any time, let's start with the chapter. So chemical bonding is the name. So let's start with essentially what bonding is. Right? So bonding can be said a way to achieve stability. Right? Now always remember in chemistry, or in fact in general as well, right? Whenever we talk about stability, right? What we essentially mean is that if something is stable, it wants to remain in its current state, right? So if I change my state to something else, if I'm very prone to change my state to something else, right? If I want to react with something and convert into something else, right? I'm not very stable, right? For stability to be high, reactivity has to be low. Think about the case of noble gases, and I think you will be able to relate these two pieces of information. Another thing is, if you take a look at it, reactivity will be low when you have an atom or a molecule or some species with a very low amount of energy. Increase the amount of energy, reactivity increases, right? So high energy, high reactivity. Thus, what can we say? High energy, low stability, right? So if you want to gain higher stability, you need to achieve a state of lower energy. So if you're currently at a higher energy, you need to lose energy to gain stability, right? So get this very clear. This is going to come in handy, right, for the entirety of chemistry. In fact, this chapter as a whole is really important for the entire chemistry going forward of 11th and 12th. All right, especially for inorganic chemistry, and then followed by organic chemistry, and relatively less for physical chemistry, but then again, it has uses over there as well. All right. Now, I teach chemical bonding in actually a very weird way. So, a very weird way is I actually bring this thing over here, this sneak peek. This is from the last session of the chapter, right? So, I'm bringing something from the last session of the chapter into the first session. I'm not going to talk in very technical terms, I'm going to talk in very intuitive terms, right? And I hope you guys understand it. If not, do let me know. As always, you guys know I do look at the chat over there, right? I do look at the responses. And by now, before I move forward, I hope you guys have done all your socializing, right? All your good evenings, all your hi, hellos, and everything, right? All the formalities are done, and we can actually focus here. All right, cool. Now think of these two as two hydrogen atoms, right? These two hydrogen atoms, all right? Now, let's say this is the nucleus and this is also the nucleus of respective hydrogen atoms. And this, what you see here, let's say this is the electron cloud. Now, what is an electron cloud? What other name can we give to it? Right? This is basically what? The orbital of the one electron of the hydrogen atom. Correct? All right. Right. So why so? Because this electron is doing some random motion around here, which we do not know anything about. Like, how is it doing the motion? We do not know, courtesy of Heisenberg's uncertainty principle. All right. So this nucleus is there and its electron is doing some random motion which we do not know about clearly. And we have another such atom over here. Right? Okay. Now these two atoms, right, they were just moving on their random paths, right? They were just moving around in this room, doing random collisions, colliding with other species in the way. So let's consider these two hydrogen atoms. Let's say they were colliding over here, right? All right. Now let's say when they were over here, right? Now think about it. When they are this close, right? This are electrons conscious? Are protons, neutrons conscious? Does proton have a brain of its own? No, right? Right? So does is there something that is telling that that is telling this nucleus, the protons in this nucleus, that look, these electrons, this electron is an electron of the other atom. Do not attract it. Is there some rule like that? No, right? So is there any law that is saying to this nucleus that look, you cannot attract the electron of that atom? No, right? These are just positive and negative charges, right? So some electrical force is going to get applied over here, and they do not have the consciousness. Correct, right? So basically, further going forward, just to since we are dealing with hydrogen atom and they're completely identical and non-distinguishable, right? So if they have the same energy, now the point is, so as to just to refer them better, we are going to name them as HA and HB, right? So let's label these as the hydrogen A atom, hydrogen B atom, correct? With that, I'll say that let's say this is nucleus A, this is electron A. And similarly, this is nucleus B and this is electron B, correct? All right, cool. Now the point is, let's say they were coming to collide with each other, right? And turns out, right, instead of going on their own way, they kind of got stuck together. Now, how did they get stuck together? Right? So in this stuck together state, right, they had a very weird dynamics playing out over here, as you can see the bundle over here. So in this dynamicity, what is happening? Right? Why is it, first of all, these two nuclei, which are both positive charge, which are a high concentration of positive charge, staying here, right? Why are they not falling apart? Right? They do repel each other, right? So why are they not falling apart? Right? Then again, this electron cloud here, right? This electron cloud, right? Why is this concentrated over here? Why is this distributed around? Electrons repel each other, so these electrons should move away as well. Right? So there are actually two types of forces being at play here. One is the repulsive forces between the two nuclei and between the two electrons, and the attractive forces between the nucleus of one and the electron of the other, and similarly nucleus of one and the electron of the other. Now turns out over here in this particular case there is a net attractive force. Right? So essentially what is happening is that even though the two nuclei repel each other and want to go away, right, there's a weird dynamic going on over here that this nucleus, right, is also attracting that electron, right, and this nucleus is also attracting this electron, right, and because of this attraction, right, they're kind of stuck together, right. This attraction is basically holding them, right, trying to bring them closer, right, and the repulsion between the nucleus and the electron obviously is trying to throw them away. Understand? And that is why even though there is a net attraction, right, it's not like these nuclei will bump into each other and merge, right? This is not going to be a nuclear reaction. Why so? Because obviously there is some repulsion between the two, right? Understand? Okay. All right, so this is what we have. Now we have basically studied the mechanisms of a chemical bond, right, in a very, very fundamental way. Now the point is, this next topic, Causal-Lewis theory, I'm not getting into it because we're going to start with ionic bond, then we're going to proceed to covalent bond, and over there I will be starting with the Lewis dot structures in Causal-Lewis theory. Then again, I just need their end result here. And I think that you guys already know this, right? The octet rule, right? So what did they finally arrive on? That atoms either need to give up electron or gain electron or share electron to achieve a stable configuration. Now what was the stable configuration, right? For most of the elements, except apart from right, a couple of elements like hydrogen, helium, or you can also talk about lithium, beryllium, or lithium, beryllium, or not boron, obviously, right? We'll get into the details of that later on, right? Except them, which basically form a duplet. Rest all the elements go for an octet, right? 8 electrons in their valence shell, right? That is basically the stable configuration. As you can also count over here, all of them in their outermost shell have a total of 8 electrons, right? Obviously now we know this is because of the fully filled S and P subshells, ns2np6. And since for one S you don't have one P, understand, right? We don't have 1p because for 1p to be there, for p to be there, L has to be 1, and for that N has to be minimum of 2. Atomic structure, quantum numbers, remember? Right? So this is what we study. Now the point is, this is all I need. This is all I need, right? So we'll study the Lewis-Throdier and Lewis dot structures and practice on them once we start with covalent bonds. All right. Now the point is, we are talking about giving up of electrons and gaining electrons and sharing electrons. So what's the case here, right? What different types of chemical bonds can we classify here? So if we have two species, one of them is ready to give up the electron, another one is ready to accept the electron. We have a very easy mechanism over here. All right, you give up, you accept. We have an ionic bond getting formed over here. Now let's say both of these species have a very strong nucleus. They have kept their electron cloud tightly bound. Neither of them wants to completely give up the electron. All right, so they're like, all right, cool. So you know what? Let's form a multi-nuclear system and let's have our electrons revolve around the collective nuclei. And that might be confusing because I went a little bit deep into the topic, right? Let's just say that neither one of them want to give up electron. Let's just share electrons. So if both of them are electronegative, highly electronegative, they will be forming probably covalent bond. Now there's also another term, coordinate bond. This we will study when we enter covalent bond as a topic. And the third one is that when both of them want to give up electron and not accept electron, we have metallic bonding, which we cover at the very end of the chapter, chemical bonding. Right? So we're going to start with ionic bonds. Right? So this is what we have. Let's start with it. Ionic bond. What do we have? Right? So basically we have essentially what? Complete transfer of one or more electrons. Obviously transfer from the electropositive one to the electronegative one. Right? And this is what we have. And the attraction over there, right, is basically the reason. The attraction between the positive ion, the cation, the negative ion, the anion is the reason for the basically what? Stability of this assembly, this aggregation, right, of the two ions over here. And this attraction itself is called as the ionic bond. Ionic bond is nothing but the electrical force, electrical attraction between these two ions. There is no actual sharing of the electron, right? All right. Also, do not always think of that bar or double bar or triple bar, single bond, double bond, triple bond whenever you hear the term bonds. No. Bonds can be of different types as well, which we'll study throughout this chapter. All right, cool. Now, there's one thing that we need to discuss, ionic valency or electrovalency. This is nothing. This is the charge on the species once they have given up or accepted the electrons, right? So let's try to see about this. Now, one thing, right? In Lewis dot structures, which we will study later on, one thing that I require here is that in Lewis dot structures, we do not represent all the electrons. We only represent the outermost shell. Mark my words, we only represent the outermost shell, not the subshell, the shell, right? That's why chlorine here has 7 electrons being displayed and sodium here has 1 electron being displayed, right? So basically we can write it as 2, 8, 1. So we are displaying this, or we can write it as 1s2, 2s2, 2p6, 3s1. So we are basically just representing this one here. Understand? right? Similarly, for chlorine, we are representing 7 electrons here. Now, what do we have? Sodium gives up an electron, gains a positive 1 charge, and basically chlorine gains an electron and gets a -1 charge. So the electrovalency of sodium is +1, chlorine is -1, simple stuff. I think there shouldn't be a problem in that, right? Okay. Let's move on to the next one. What do we have over here? All right, calcium is there. Calcium is giving up both of its electrons in the outer shell, becoming Ca2 plus. So the electrovalency of Ca is 2 plus in this particular compound, CaCl2. Similarly, for chlorine, since each chlorine is gaining 1 electron and gaining essentially a charge of -1, its electrovalency becomes that itself. Pretty simple stuff till now, right? No issues should be there. Let's move on, right? So for the formation of an ionic bond, what do you think should be the parameters? Now, one of the most obvious parameter is that the atom which is going to become the cation, right, that should be readily available to give up electron, right? All right. Similarly, the atom which is going to become the anion should be readily able to accept electrons. Now, what does that mean? Right, so lithium here, let's say, should easily be able to lose an electron, right? All right, although we'll later study that lithium actually, because of its very small size, actually shows some resistance to losing an electron completely. But for now, let's go forward with this case, right? So the species which is going to be the cation should have a low ionization energy. And the species that is going to gain the electron should have a high electron gain enthalpy, right? So very low amount of energy should be required in removing an electron. A very high amount of energy should be released on gaining that electron. And the third one here, Le, what is this? So this is lattice energy. We have not studied it yet. Let's dive deeper into this term. All right, now to understand lattice energy in a better way, let's try to think of an analogy, right? Let's try to think of something that is slightly oversimplified, right? Then again. So let's say I'm in this room, right? And let's say from this corner, right, a couple of A plus gaseous ions have been released, right, into the room. Let's imagine them like bees coming into the room like in flocks, right? So let's say from this end of the room, a lot of, let's say 1 million A plus gaseous ions have been released. All right, cool. Now let's say from the other end of the room, right, 1 million B minus gaseous ions have been introduced in this room. Now what will happen? Right? Let's say one A plus is there. It was doing its random collisions and it got in the vicinity of a B minus. Now because of the electrostatic attraction, what happened? They got stuck together. Correct? So now you have A plus, you have B minus, but for this A plus, except this area where there is a B minus, all the other regions are exposed, right? So from that in, another B minus got stuck to it from top, another B minus got stuck to it from bottom, another B minus from front and from back as well, right? So you have 1, 2, 3, 4, 5, 6 B minus attached to it. Now consider the case of this B minus, right? For this B minus, only this side, right, is basically in touch with the A plus, right? All the other sides are exposed. So from there, an A plus gets stuck, an A plus gets stuck, an A plus gets stuck, and so on and so forth. Now you get where the picture is going, right? Obviously, we are going to keep building on an arrangement that basically, accumulates on top of these. And you have a giant arrangement that comes out of it, right? So in a way, right, what we have here, this arrangement, this is called as a lattice, right? Now, obviously, in this process, there will be some energy release, right? There are going to be attractive forces between the positive and the minus, and there's going to be repulsive forces between the similar charges as well. And then again, there is going to be a net attraction, and because of that, there's going to be a release of energy, which can be called as the lattice energy. But then again, right, lattice energy could have different values, right? Depending on whether I have 100 A plus and 100 B minus, or I have 1 million A plus and 1 million B minus, or I have some other amount. So we standardized it. We said, all right, we are ultimately forming 1 mole of the lattice. All right, okay, cool. So when we have 1 mole of the lattice being formed from its constituent gaseous ions, right, the energy released in the process is called as lattice energy. Right? Okay. So the energy released, right? Now always when the energy is released, right, mathematically we represent it in a negative way. For example, let's say initial energy combined of this and this was, let's say, 100, and let's say the total energy of this formed was, let's say, hypothetically 60, right? What is the delta here? What is the final minus initial here? 60 minus 100, that is minus 40, right? So there is a release of 40 units of energy, or we can say the energy change of this process is minus 40. So whenever we have minus 40, right, or some energy kilojoules per mole or some other unit written over there, we are talking about the formation of a lattice, because then only the energy is released. We can also think of this in one more way, right? So I forgot to mention one point, right? We are bringing these positive and negative charges from infinity together, right? We are bringing them together from a point wherein initially they were not experiencing any forces on each other, right? Okay. There's one more way. How about we take 1 mole of a lattice and break it, right? So then again, the energy required to break 1 mole of a lattice into its constituent gaseous ions to a point at which the gaseous ions do not experience any force on each other, right, can also be called as lattice energy. But this time around, you will be providing it some energy. So this time around, the delta will be positive. So when you are provided lattice energy with a positive value in a particular question, let's say, we are actually talking about breaking the lattice. Understand? Okay, cool. Right? So basically, we can depict lattice energy either of these two ways, either the breaking of a lattice or the formation of a lattice, right? Depends, the values will change, but we are mostly concerned with the magnitude. The signs are just for our understanding, to basically understand what the question is trying to convey, whether the question is trying to say the breaking of a lattice or the formation of a lattice, right? The breaking of a lattice, positive value, or the formation of a lattice, negative value, right? But we are mostly concerned with the magnitude of it. All right, cool. Right? So the point is, now think about it, right? Lattice energy, right, will be higher if you have a very compact and strong lattice, right? If the electrostatic attraction is really, really strong, right? So naturally, it depends if the lattice is compact. So it depends on the inter-ionic distance. It depends on the inter-ionic distance. Let's say this is positive, let's say this is negative. It depends on the inter-ionic distance, right? Now, if the inter-ionic distance is large, right, you do not have a compact lattice. You do not have a good electrostatic attraction over there. And essentially, you have a weak lattice, so the lattice energy is inversely proportional to the inter-ionic distance. Inter-ionic, right? Think about it. Inter, what does inter mean? Think about it from this way. An inter-class competition is an intra-school competition. Think about what I just said. Think about a competition between different classes of your school, or think about a festival in which all of you have been asked to hold or stand some stalls where you are preparing something and someone is buying something. Let's say those competitions, right? So an inter-class competition is an intra-school competition. So we are talking about inter-ionic distance. We are talking about the distance between the positive and the negative ion, right? We are talking about the distance between their center of masses, right? All right, or the internuclear distance of these two oppositely charged ions. Okay. Further, if the ions have a good amount of charge on top of them, for example, if instead of +1 -1 we have +2 -1, or we have +2 -2, right? It will be a stronger lattice, and so it also depends on the charge on the anion and the cation. All right, so you have a larger charge, you have a greater charge, you have a stronger lattice, you have a higher lattice energy being released by the formation of a lattice, or more energy required to break the lattice. Understand? All right. Right? Now the point is, you can take it in this way. In all of these examples, if you take a look, we have +1 and -1 charge. So, right? So the charge factor is the same in all of them. What is happening is the inter-ionic distance is increasing, right? And because of that, the lattice energy is decreasing. Now, do not think in the exact numeric sense, just consider the magnitude of them. The magnitude is decreasing, right? So the third one here, this requires lesser amount of energy to break the lattice, or we can say lesser amount of energy is being released by the formation of this lattice. All right, so this is what we have. Now then again, if you consider another example, let's say NaF and CaO, we have +1 charge and -1 charge here, and we have 2 plus charge and 2 minus charge here. So then again, what do we have? More charge, more lattice energy, and then again you can compare the magnitudes and see what I'm trying to say. If in case you're confused in a particular question, well, you're trying to answer the trends, the question is asking you which one of the two will have a higher lattice energy, and you're confused, right? As to, because one has a higher charge, but the one that has a higher charge also has a higher radius, right? If the change in radius or the inter-ionic distance is not that much, give the preference to charge. Understand? So, right, so the charge trend, right, stands over the inter-ionic distance trend. Right, so this is what we have. Now, the third factor is coordination number, right? Coordination number is essentially, look, what can happen is that I can have a certain ion, certain cation, certain anion of a certain radius. Now, I can arrange them in a particular way, which is not that compact, and basically this lattice has a lot of void, has a lot of empty space within, right? Now I can also just compress this, right, and get as a result a more compact structure, and that compact structure will be a stronger lattice. So in the compact structure, right, the cation will be in touch with more anions and the anion will be in touch with more cations. And that indeed is called as coordination number. As you would have read by now, the coordination number of cation is the number of anion, right, that are the first neighbors, that are the first neighbor of this ion, right? All right. Similarly, coordination number of anion can be called as number of cations surrounding the anion in a similar way. But then again, coordination number is not so important of a factor. It is only applicable in the case of sulfates and carbonates of alkaline earth metals. So look, we are not God, right? We didn't create molecules, we didn't create atoms, we didn't create ions. We're just trying to create some rules by which we can predict between two substances which one will have a higher lattice energy, right? Now, in these cases, those rules do not apply. So we realized, all right, so this is because of this logic, right? So we'll see it in a bit. Just think about it. If the cation is huge, larger, it will be in touch with more anions, right? So if the size of the cation increases, the coordination number increases, and with this third factor, the lattice energy increases. You can develop a similar logic for the size of anion as well. But in these cases, the sulfates and the carbonates of alkaline earth metals, which group is it? Second group, obviously, right? In this particular group, what happens is that if you go from here to here, you realize that SO4 is the same, so you do not need to worry about the size of the anion here. But if you look at it over here, right, so from beryllium to barium, the size of the cation is increasing. So by the normal logic of interionic distance, lattice energy should decrease, right? But in this cases and the cases of group 2 carbonates, right, the reverse trend is possible, and that is explained on observation from various experiments that has been explained with the help of coordination numbers. Right? So this is what we have. Now let's move on to the next topic, solvation energy. What we are going to do is, once we are done with solvation energy, we are going to club these two and we are going to end up with an interesting conclusion which deals with playing around with lattice energy as well as solvation energy. But before that, let's try to understand what solvation energy actually is. All right. Okay. All right. Oh, one more thing I forgot. So to study solvation energy, then again, we need around 2 to 3 minutes of time on covalent bonds. I need you to just, just get acquainted with the concept. Now look, right, in this case that we did in the beginning of the session, right, we had the same atom, right? Not the same atom, we had atoms of the same element. Their nucleus were equally powerful. And so here, as you can see, right, the electron density is uniformly distributed, right, on either sides. Throughout the, around these two nuclei, the electron density is uniformly distributed. Right? Each nucleus has the same electron density, right, distribution around it. But what if one of this nuclei was relatively weaker or less powerful and another one was relatively more powerful? Then we can say that the electron density will be more focused around the more powerful nucleus. What am I trying to say? What I'm trying to say is that, look, right, in this cases, in this arrangement, in this dynamic arrangement of attractive and repulsive forces, if one nuclei is more stable, is more stronger, right, it will hold more electrons around it. Now, obviously, I do not mean stationary holding. I just mean that the shared electrons will be spending more of their time around the more powerful nucleus, right? So let's try to understand with this with the help of an example. Let's say I'm going to take a hypothetical example. So let's say I'm dealing with let's say a bond of H and Cl, right? This is not hypothetical, but to call it completely covalent is also not entirely correct. That you will understand as we go on to session 3 and session 4 and so forth, right? You will understand more of what I'm trying to say, right? Now, essentially, if you take a look at it, in fact, you know what? Just let's take it as fluorine only, right? All right. So we know the atomic number here is 9. So we know that there should be 9 electrons in a region around it, right? And we know that hydrogen has an atomic number of 1. So there should be 1 electron around it. Correct? Now, turns out, right, in some of the situations, right, they share 1 electron. So basically, if you took different snaps of it, I'm going a little hypothetical here. Let's say we took different snaps of the nuclei of hydrogen and the space around it. In some of the snaps, we found 1 electron. In some of the snaps, we found 2 electrons, because that is the shared electron of fluorine, right? All right, cool. Similarly, if we took the snaps of the nuclei of fluorine and the space around it, in some of the snaps, we will find 9 electrons, but in some of the snaps, we will find 10 electrons, because that is the shared electron of hydrogen, right? Because this collective set of 10 electrons is moving around in the space around this set of 2 nuclei, correct? All right. Now, the point is, right, if one of the nuclei is more powerful, as we have over here, what's going to happen is, right, we are going to find more snaps in which we have 10 electrons around the fluorine nuclei as compared to if we had fluorine bonded together, right? In that case, we would have uniformity, right? So in this particular case, because the fluorine nucleus is relatively more powerful, we are going to find more snaps relative to this case in which there are 10 electrons around the fluorine nucleus, right? The electrons like to spend more time around the more powerful nucleus because of obvious reasons, attraction, right? So what's going to happen is that essentially we can say that in HF, right, we can say that there is a slight negative charge. It's not a complete -1, right? You can think of it in a very simplified way, an oversimplified way, to be an averages over time. So you can say that yes, there is a 0.000 negative of, let's say, 5 charge here, right? Because the electrons like to spend more time over there. And similarly, we have plus 0.0005 charge over here because the electron like to spend less time over here relatively given the more powerful nucleus. And because of that, there is a slight positive charge on fluorine and there's a slight negative, there's a slight negative charge on fluorine and there's a slight positive charge on hydrogen. We will study this later when we come on to dipoles in covalent bonds, but for now, this knowledge is enough. So what we do is we instead represent this in this particular format, del minus, del positive, right? Whenever I say del, for now, just read it in your head to be slight, very slight negative charge, del minus, very slight positive, del plus charge, right? All right, cool. This is what we have. Now, in a similar way, when we talk about, for example, H2O, what happens is that oxygen obviously is more electronegative. So oxygen gets a del negative charge and hydrogen gets a del positive charge, right? Now, keep in mind, right, I don't mean an exact value by del, right? I don't mean this value 0.0005. I just mean a very slight value, right? So the del over here, right, this del and this del, they do not need to add up and come out to be 0, right? They are not the same del. I'm just using a very vague term, del, to say slight negative and slight positive charge. But yes, indeed, the overall molecule will be neutral. So this charge, this slight positive charge plus this slight positive charge plus this slight negative charge will indeed come out to be 0. All right. Slightly confusing. Let's move on and let's try to understand how this is going to help us understand solvation energy. So think about it. We have this crystal here, right? And let's say we drop this crystal in a bucket of H2O. Right? So we have this crystal and we dropped it in a bucket of H2O, right? So let's say this is now inside a beaker. Now what's going to happen is, right, because of the del positive charge of hydrogen of H2O, they are going to get attracted, right? They are going to get attracted towards the Cl minus, correct? And in fact, going forward, I might just, represent this in this format, H2O in this format. I might sometimes in this Wix shape, right? I might just write it as del plus and del minus or just represent it like this. All right. So now what is happening over here is that essentially, right, a lot of H2O molecules have aggregated over there because the del plus of hydrogen is being attracted by the Cl minus, right? And I'm drawing only 3 over here, but think about them as a million H2O being accumulated over there, right? Not only in a single layer, let's say a single layer is there, then a second layer is there, let's say a third layer is there, let's say a fourth layer is there. And in fact, later on, you'll study that there are actually 2 types of attractions here, but we are only considering the electrostatic attraction. So we are just considering one type of layering. All right, not in our syllabus till now. We will study that second type of layering, that second type of attraction that is going on here in the chapters in 12th standard when we come to complex formation. But now let's stick to it. We are only going to study electrostatic attraction. So let's say around the Cl minus, right, a single layer is there, let's say with 10,000 H2O molecules being attracted to the Cl minus. Then there is a second layer, then there is a third layer, a fourth, fifth, sixth. Obviously, as we go further and further, the layers are less and less weakly held, right? All right. So there's this entire entourage of H2O molecules accumulated around it, right? Now, obviously, the del plus of one H2O molecule, the del plus of one H2O molecules, right, will be, let me draw it in this way, will be attracted with the del minus of another H2 molecules, right? So not only they are being attracted by the Cl minus, right, they also have an attraction with other H2O molecules, right? So you understand there is a whole party going over there with a lot of H2O molecules which are getting attracted to the Cl minus, but at the same time the remainder of the H2O molecules are also trying to pull these H2O molecules towards them, right? So as a collective effort, what happens is that this Cl minus gets pulled out. Or you can also think of it in terms of Na plus as well. For example, right? So let's say a lot of H2 molecules with O point towards it, right, has an accumulation over here. And I cannot possibly draw all of the H2 molecules, right, on all of the ions over there. So I'm just trying to draw the representative ones at least, right? Only a couple. Right, so in a way what happens is this is not the most accurate representation. Think of the H2O molecules being in millions, right? And because of that, they start pulling this lattice apart from all sides. Not just the corners, from all sides they start pulling this lattice apart. And so essentially, eventually, in certain scenarios, giving certain conditions, which we are going to study, they end up breaking the lattice. Right? Okay. Cool. So this is what we have. Now the point is, right, in this particular process, energy gets released. Why so? Because when they do pull it apart, right, they expose more of the surface of the Na plus or the Cl minus, which now can be further surrounded by other H2 molecules, and over time they form a solvated radius around it, right? They form a whole solvation, a solvated accumulation around the ions, right? As has been depicted here. But then again, in this scenario, right, just multiply the number of H2O by a million, let's say, right? And one more thing, wherever you have minus, they actually mean del minus. Wherever you have plus, they actually mean del plus. All right. Now what's going to happen is, imagine, let's say 10,000 H2O on the surface, right? So on this surface, what's going to happen is, right, if you consider this surface, right, the total charge of the Cl minus is -1, right? But let's say because of all the del plus, right, all the del plus of the H2O, right, in the dotted circle is coming out as a summation of, let's say, plus 0.2, right? And where is that happening? Let's say we have a lot of H2O molecules, a lot of H2O molecules over here. A million, remember I said even more than that in some cases, right? So on the outer surface, right, because of the del minus of the oxygen, that minus point charge has been protruded, right? Understand what I'm trying to say? So there's this Cl minus and there's a lot of sort of an accumulation going on over here, multiple layers. So the outermost layer is going to have a lot of oxygen atoms protruding out, which are a part of H2O molecule. Obviously, we are not breaking the covalent bond. So on the surface, there are going to be a lot of oxygen atoms with a lot of del minus on top of them. So essentially what has happened over here is that if you consider, right, this Cl minus and the dotted circle, right, the charge inside it has reduced from -1 to -0.8, and that extra negative charge, that gap of a negative charge has been spread around on the outermost surface of the entire solvated accumulation of the entire solvated sphere. Understand? Right? So in a way, this is called as charge diffusion. Right? We have diffused the charge. The charge was initially concentrated on a single Cl minus ion. Now it is diffused on the surface. Now you'll study later in physics that whenever you decrease the concentration of charge, right? You diffuse the charge, right? You achieve more stability, and therefore there is a release of energy, which is called as solvation energy. Now, there will be two types of solvation energies, the solvation energy of the cation and the solvation energy of the anion, and the summation of the two will essentially give you the total solvation energy. All right, cool. Right. Now, most of the cases will have hydration. In fact, the previous slide also had hydration written on top of it. So the point is, many times we have, in most of the cases, we have H2O as the solvent, right? So instead of saying solvation energy, right, when the H2O is solvent, again and again, solvation energy when H2O is solvent, solvation energy for NaCl when H2O is solvent, solvation energy for KCl when H2O is solvent, and again, we just rename the term as hydration energy. Understand? All right, cool. Now the point is, right, if you look at it over here, what do we have? We have essentially, if you look at it over here, right, in this particular side, if you look at it, right, this is essentially what? Breaking a lattice in its constituent ions, right? And what do you have over here? We have basically what? A plus gaseous. Then what do we have? We have B minus gaseous. And where is it going? It's going to A plus aqueous and B minus aqueous, right? Understand? Right? So this is basically what? The hydration process. Right? So what is the lattice energy process? You take ions in their gaseous state and you form a solid lattice. Right? Okay. Now what is the solvation or the hydration process? The hydration process is you take ions in the gaseous state, right? And essentially what do? You form solvated or hydrated ions depending on what the solvent is. For example, if we had alcohol over here, instead of aqueous, I would have written A plus bracket alcohol AlC. Right? Okay, cool. Now, right, solvation energy obviously is solvation energy of cation plus solvation energy of anion, right? So it basically is the summation of two things. So this is the component, right, which has come from the solvation energy of cation. Solvation energy cation will be more if the cation is small, will be less if the cation is large, right? More accumulation can happen if the cation is small, right? Similarly, for the anion as well, we have this. If we had a smaller anion, more H2O or more solvent molecules could accumulate around it. If the size was larger, less could accumulate around it, right? And so in both the cases, if we have a smaller radius, more energy is released. If we have a larger radius, less energy is released. And this is what we have. Now the point is, one more thing is there. Then again, we are talking about, let's say Cl minus, right? So H2 molecules are being attracted over there because of their del plus on hydrogen. So instead, if I have a higher negative charge, a greater negative charge, obviously the attraction will be more, right? It's quite possible, let's say, hypothetically, instead of 10 layers in the case of Cl minus or -1 charge, let's say we have 13 layers hypothetically in the case of 2 minus charge, right? So then again, you understand, right? So if you increase the charge, more accumulation of those solvent molecule layers is there, and thus more energy is released, right? So then again, it is proportional to the charge on the cation and the charge on the anion. Then again, charge dominates the size trend. Now in this case, we have the same element. So let's say in all three charges, right, it has the similar charge or the same charge, similar size or the same size. So with the same size or similar size, if the charge is increasing, what can we say? We can say with certainty that for a higher charge, more energy, more solvation energy has been released, right? Okay, cool. Then further, right, there's another point over here, dielectric constant. You do not need to get into it. There might be a very straightforward question with a couple of solvents being provided along with their respective dielectric constant values, and you might be asked that this compound will have the highest solvation energy in which particular solvent. So think about it. If you have higher value of this, then you have a lower value of this, right? But if you subtract even lower value from 1, the overall value turns out to be higher, right? Think about it in this way. I'm just assuming some hypothetical numbers. Where do you get an overall higher number, right? We have 1 by 2 and we have 2 by 3, obviously, right? So if this dielectric constant of the solvent is higher, right, this entire expression turns out to be higher, and you have a higher solvation energy being released, right? So it also depends on the nature of the solvent. Now, final thing that we need to consider is that turns out we thought, all right, so this is, let's say, our cation, or we can also talk about anions, but let's say this is our cation, and it has, let's say, 10-15 layers of solvent around it. It has formed a big jumbo aggregation sphere over here, right? Okay. Now somebody asked me, right, tell me something about the ionic radius of, let's say, lithium plus and Na plus. So I'll be obviously like, all right, so lithium plus has a smaller ionic radius. But let's say somebody tells me or asks me about the hydrated radius or the solvated radius. So this time around, I'm asking not about the radius of the lithium plus ion, but rather the radius of the entire solvated aggregation that has been formed around it. Now it turns out when you have more charge concentration, right, even if you have smaller size, the hydrated or the solvated radius turns out to be larger, right? So between, let's say, if we talk about ionic radius, we will say that obviously lithium plus has a lower radius, right? Sodium plus has a higher, right? Potassium has a higher, and we can go on in this particular way, right? But if we talk about the hydrated radius, right, the lithium plus is going to have, right, the maximum hydrated radius, followed by sodium plus, followed by potassium plus, followed by rubidium plus, followed by cesium plus, followed by francium plus, right? Understand? Right? So the smallest size, given that all of the species that we are considering have the same charge, the smallest size has the highest radius. Understand? Okay, so this is what we have. Now then again, what happens is that, let's say, when you're talking about, let's say, mobility of ions. Now, on the next slide, it will get more clear. But let's say we are talking about how an ion moves inside a particular solvent, right? So in that particular case, right, it's not just the ion that is moving, it's also carrying all that bunch of solvent molecules which have been accumulated around it, right? So the one with the highest hydrated radius is the most bulkiest to move around, and so mobility of the ions or ionic mobility follows the same trend, that for the same charge, the smallest ion has the highest hydrated radius, so it is the most bulkiest one, so it will be the slowest one, so it will have the lowest ionic mobility, and this is exactly what we have here, right? All right. Now, in a similar way, right, this is basically something that you will study in your 12th standard, but think about it. What is current? Is current the rate of flow of electrons? Many of you might be nodding right now. Think again. Current is the rate of flow of charge. And so inside the solution, what is completing the circuit here? Are electrons jumping from one plate to the other? No, it's because of the movement of ions, right? So the ionic mobility, right? The ions move, and because of their movement, there is a flow of charge from one end to the other. So the ionic mobility actually factors into the conductance, right? So if somebody asks you about the conductance, obviously the slowest ion, the one that has the bulkiest aggregation of solvent molecules around it, is going to have the lowest conductivity. Understand? Right? So similarly, this also follows the same trend, and this is what we have. Now this was it for today's session, right? Try to understand it. Ask your doubts. I'm here, right? The session is not ending, right? I'm just going to blabber some things just to pass the time. In the meantime, ask your doubts. Because in the beginning of the next session, in fact, for the first half of the next session, we are going to club these two and we are going to identify solubility trends. We are going to consider, all right, we have this compound. Now, what do you think, right? Between, let's say you have these two compounds. Now, what do you think? Which one will be more soluble? Right? So you're going to consider the solvation energy and the lattice energy trends, and we're going to figure out for which one, right, the solvation energy is even more than the lattice energy in the two cases, or even less in the two cases. Understand? Right? So all of that we are going to do in the next session. We are also going to study something called as covalent character in an ionic bond, right? No bond is 100% ionic. There is a slight discrepancy into it, right? Till now, we have been studying the ideal cases of ionic bonds wherein one has a +1 or +2 charge, the other has a -1 or -2 charge, and we have a perfectly ionic bond. But not all compounds, all ionic compounds are 100% ionic. We have observed some sharing of electrons in some cases. That is also something that we are going to discuss in the next session. So all of that is going to require the knowledge that you gained today about ionic bonds. Lattice energy, solvation energy, really, really important. Come having revised that, and on top of that, revise periodic properties. Revise effective nuclear charge, revise radius trends along the period, S and P as well, D as well, down the group as well, within D as well, right? Remember all that. Try to revise and then come for the next session all prepared. And so solubility and covalent character in an ionic bond is going to be a cakewalk. Trust me. Right? So, all right, this was it for today's session. We'll meet again in the next session.